Okay, now let's see how we can design a bandpass filter. So here we want to talk about designing bandpass filter with cutoff frequencies equal to omega C1 and omega C2. In order to design a bandpass filter and making sure if the cutoff frequency that I have for bandpass filter are widely separated, so if the given omega C2 and omega C1 are widely separated, which means that omega C2 is much greater than omega C1, then each step of cascaded circuit can be designed separately. Otherwise, you have to use the equation that we had in previous slide, this equation. Then you have to use this equation and come up with a solution for your parameter. But here I want to show you how you can design your bandpass filter if your given cutoff frequencies for bandpass filter are widely separated. In this scenario, you can design each circuit separately. So first, I'm going to focus on my low pass filter. So I'm going to focus on low pass filter, and I know that the cutoff frequency of my low pass filter, which is X, and that's equal to 1 over RL multiplied by CL, should be equal to the higher cutoff frequency, should be equal to omega C2. So my omega C2 is going to be equal to 1 over RL multiplied by CL, and that means that I can calculate my RL and CL here. The next step is focusing on the high pass filter. So for the high pass filter, assuming that the cutoff frequency is Y, that's going to be equal to 1 over RH multiplied by CH. So this time I know that because the frequencies are widely separated, so omega C1 and omega C2 are widely separated, I can assume that omega C1, or the smaller cutoff frequency, is equal to my high pass filter cutoff frequency. So it means that here I can calculate or compute my RH and CH. And finally, my last step is focusing on the gain. So based on the gain that I need for my bandpass filter, I can compute my RF and RI. So this gain should be equal to minus RF over RI. So I have to choose values in a way that the ratios satisfy the required gain. Now you might ask why I'm assuming that the gain is equal to the gain of the inverting amplifier. I can refer you to the equation that we have here. Here we know that the gain is equal to what we have in numerator for the standard form of bandpass filter transfer function is basically K. Let me delete some here. So what we have for the numerator of a standard bandpass filter transfer function is basically K multiplied by beta multiplied by S. So looking at numerator here, what I have is minus RF over RI multiplied by X multiplied by S. Now, what is my beta? My beta is X plus Y. But because I'm assuming that X is much greater than Y, I can say X is also somehow equal to X minus Y. So these two are not too much different. So for example, if X is 1000, then X minus Y, which is 998, is going to be very close. So I can replace x by x minus y, and then it means that here I have beta. So if I match the coefficient here, then it means that my gain is minus Rf over Ri. So the gain can be described by the gain of my inverting amplifier. Okay, let's go back to the design. I want to solve this example. So let's assume that we want to design a broadband op-amp filter. So, okay, let's look at this example. So here we are asked for designing a broadband passband op-amp filter. Okay, the op-amp filter means that we are looking at an active filter, and we want to have a passband filter. And this broadband here means that we are choosing our cutoff frequency to be widely separated. So it means that we have a broadband filter here. And the parameter of the filter that we are looking for are as follows. So we need to have a gain equal to 2, and we need a cutoff frequency f1 equal to 100, and our f2, the second cutoff frequency, equal to 10,000. Here you can see that the cutoff frequency are broadband, so f2 is much greater than f1. That's why I can say that f2 is equal to the low pass filter cutoff frequency, and f1 should be equal to the high pass filter cutoff frequency. Now, let's follow the steps. The first step is focusing on the low pass filter. And for low pass filter, we know that the cutoff frequency is equal to 1 over RL multiplied by CL. Okay, before I forget, we are asked in the example to use only capacitors equal to 0.2 microsecond. So this is also given. So we cannot use any other capacitor value in our design. We only have access to capacitor with this particular value. Okay, so in low pass filter, the cutoff frequency is equal to 1 over RL multiplied by CL. So I know that I have to use a capacitor which has value equal to 0.2 microfarad. And this is going to be my low pass filter frequency, which is supposed to be equal to f2, so it should be equal to 2 pi f2. So it means that I have omega 2 here. So solving this equation, I can find my RL. So RL should be equal to 1 over 2 pi multiplied by f2, which is the higher cutoff frequency, and that's 10 to 4, and multiplied by 0.2 multiplied by 10 to minus 6 to consider the micro. If you do the calculation, you're going to have RL equal to 80 ohm. Okay, now let's go to the next step, which is now let's go to next step, which is designing the parameter of the high pass filter. For the high pass filter, again, we know that the cutoff frequency is equal to 1 over RH multiplied by CH. And this time, this cutoff frequency for the high pass filter should match the cutoff frequency, the smaller cutoff frequency, which is F1. So it should match F1, So we have 2 pi f1 here, which is basically our omega 1. So omega 1, or the smaller cutoff frequency, is equal to the cutoff frequency of high pass filter. Now again, we know that CH can be only equal to 0.2 micro, and we have f1 as 100. So we can solve for RH. So RH is going to be 1 over 2 pi multiplied by 100 multiplied by 0.2 multiplied by 10 to minus 6. So after solving, we're going to have RH equal to 7,958. So right now I have the parameter of my low pass and high pass filter. So the last step is focusing on the gain. So the third step is focusing on the gain, and let's assume that my gain is equal to 2 because that's what the problem is asking for. So it means that RF divided by RI needs to be equal to 2. I can choose any values that I need. So let's assume that I'm choosing my RF to be 2K and my RI to be 1K. As long as the ratio satisfy my equation, that's correct. So based on the values that are available, for example, in a lab, I can choose a set of resistor to satisfy the gain equation. And then the very final step, which is not designing, but just showing how the circuit looks like and adding the parameter into the circuit. So I'm going to show you how this bandpass filter looks like here. So this is going to be my bandpass filter circuit, in which the input voltage will be applied here. So here I have my VI, and the first circuit is going to be my low pass filter, and I know that the resistor of low pass filter should be equal to 80. So here I have 80 and here I have 80 as well. The high pass filter circuit has a resistance equal to 7,958. So for both resistor, I have to use the same value in order to have a gain equal to 1. And then my capacitor values are supposed to be 0.2 micro. So same here. And finally, for my inverting amplifier, I've chose to have an input resistor equal to 1K and an output resistor, feedback resistor, and my feedback resistor to be 2 kilo ohm. So, and here is what I consider as my output voltage. So this is how the design of a broadband passband filter looks like. So here I have a bandpass filter, and this bandpass filter is broadband because its cutoff frequencies are equal to 2 pi multiplied by 100 and 2 pi multiplied by 10,000. So they are widely separated, and that's why I can assume that the lower value should be the value of the cutoff frequency of my high pass filter, and the greater one is supposed to be the cutoff frequency of my low pass filter. If this assumption is not correct, so at the beginning when you are trying to design, you don't have this assumption of broadband. Sometimes you have to decide if the frequencies are showing you a set of widely separated frequency or they're not. So if in this problem I tell you that I'm looking, for example, for 100 and 10,000, you can decide that these are widely separated, so you can follow these steps. If they are not, so let's assume that I ask you for 100 and 200 as the cutoff frequency, then they are not widely separated, and in order to design, what you need to do is using the actual transfer function of this combination, which is what you have here. So this is what you need to focus on and design based on this equation. So here you saw the design of a bandpass filter with widely separated cutoff frequencies. In another video, I'm going to show you how you can design a bandpass filter which does not have widely separated cutoff frequencies.